Alright, hello everyone, my name is WenTao Zhang. Today we will be talking about chapter 2.2, limits involving infinity, right? So we will be focusing on the following topics. They are finite limits as x approaches positive or negative infinity, infinite limits as x approaches a value a, and end behavior models, right? So let's begin by talking about finite limits as x approaches positive or negative infinity. These limits are exactly as their title suggests, right? We use infinity to describe the behavior of a function with values in its range or domain when the values in its range or domain outgrow all finite bounds, right? Now, before we go even further, I need to clarify that infinity is not a number; it's a concept. Okay. You will make a fool of yourself if you try to, if you ever call infinity a number, right? So when we say that the limit of f of x approaches infinity, we mean the limit of f of x moves increasingly far to the right of the number line, right? When we say the limit of f of x approaches negative infinity, we mean that the limit of f of x moves increasingly far left, right, of the number line, right? So the limit in each case may or may not exist, so do bear that in mind, okay? So let's look at an example. Example number 1, this is, again, straight out of your book. And the objective of example number 1 is looking for horizontal asymptotes, right? You may remember this from Algebra 2, and thus far you may be wondering why you signed up for calculus when you have learned everything in Algebra 2. Well, let's just say that calculus will explain why everything works in Algebra 2. Right, so the question reads, use graphs and tables to find the limit as x approaches infinity, positive infinity, of f of x, and identify all horizontal asymptotes of f of x equals x over the square root of x squared plus 1. Well, I have conveniently provided this graph for you. I actually took this, again, straight out of the book, so nothing new. I even have the credits right here. But anyways, so let's look at this, right? Alright, so I have graphed the equation, and I told you I'm not a big fan of graphing, but you know, that's what the question required, so I did it. So the graph climbs rapidly towards the line y equals 1, right? As x moves far away from the origin to the right, right? X is going that way. On our calculator screen or on this sheet of paper, the graph soon becomes very indistinguishable with the line, right? With the line y equals 1. Thus, the limit, right? The limit as x approaches positive infinity of f of x, right, equals 1, right? Because as you go really far out, like if you go like really far out, then these two lines will be indistinguishable, right? Right here they may have some difference, but there's not much difference at all, right? Similarly, as x moves away from the origin to the left, right, if you move this way, then the graph drops rapidly towards the line y equals -1, and then it evens out, right? And soon appears to overlap the line as well, right? Overlap the horizontal asymptote y equals -1 as well. Thus, the limit as x approaches negative infinity of f of x equals -1, right? So the horizontal asymptotes are y equals 1 right here, and y equals -1 right here, right? And that's not too hard. So next we're going to talk about infinite limits as x approaches some value a, right? Now the values of a function f of x outgrows all positive bounds as x approaches a finite number a. We say that the limit as x approaches a of f of x equals positive infinity, right? Now, if the value of x becomes large and negative and exceeds all negative bounds, then as x approaches a, we would simply jot a negative sign in front of here, right? So, so now we're going to do an example, right? And we're going to look at an example that deals with vertical asymptotes, right? So, as infinite limits as x approaches a, you're often going to find vertical asymptotes, right, to describe the behavior of your function. So we look at the vertical asymptotes of f of x equals 1 over x squared, right? And we have to describe the behavior to the left and right of each vertical asymptote. So what we do here is we take two separate limits, right? So I'm going to cross that out here. All right, so this is example 4, again, from the book. Okay, so what we're going to do here is we're going to take the limit, right, as x approaches 0 from the right-hand side of 1 over x squared equals infinity, right? And because if you plug a number very, very small in here, right, you're going to get 1 over some really small number, which is going to be some very large number, and we denote that with infinity, right? And similarly, right, we do limit as x approaches 0 from the right-hand side, right, or from the left-hand side, excuse me. And we have 1 over x squared equals infinity as well. Because however negative your number might be, maybe it's like negative 1 times 10 to the 50th power, right? It's squared, right? So it's still going to be some really, really, really small number. And 1 divided by a really small number is a really large number. And we, once again, denote that with infinity. So the line x equals 0 is the only vertical asymptote, right? Because if you guys don't know what the graph looks like, it looks somewhat like this. It's like the 1 over x function, but, you know. Yeah, so this is where your vertical asymptote is going to be, right? It's going to be exactly, oh, sorry, here, let me zoom out a bit. It's going to be exactly on the y-axis, right? Okay, all right. So let's move on and and let's talk about other concepts. So we are going to move on and talk about end behavior models, right? And you're going to ask what end behavior models are. Well, for numerically large values of x, we can sometimes model the behavior of a complicated function by a simpler one that acts virtually in the same way, right? So for example, in example 6, right, once again, out of your book, example 6, you have f of x equals 3x to the 4th minus 2x to the 3rd plus 3x cubed minus 5x plus 6. Whew. And then you have g of x equals 3x to the 4th, right? Now, you have to show, no, okay, so the question asks us to show that while f of g are quite different numerically for small values of x, right, so f of x has so many terms that, of course, this would be greater than this when you plug in like 100, right? But when you go on a larger scale, a much more grander scale, these two are actually quite similar. We can test that by taking the limit, right, as x approaches positive or negative infinity, that doesn't matter, of f of x, right, over g of x, right? And so what you're doing is you're basically dividing this by this, right? And what you do is you divide by the highest term, right? And here, I'm going to write this out, so minus 2x to the 3rd plus 3x squared minus 5x plus 6. And you have 3x to the 4th. When you divide, this is what you get. You take the first term divided by this, you get 1. Take the second, divide, you get 2 over 3x. Take this, divide by that, and you get plus 1 over x squared. And I'm just going to write out the rest. 5 over 3x to the 3rd plus 2 over x to the 4th. Right? Now, you should be convinced that since all the x's are on the bottom, as x approaches a really large value, right? This is going to be 2 divided by some huge value, and that's going to be 0. This is going to be 1 divided by some huge value, that's going to be 0 as well. This is 5 divided by some humongous value, since you actually have to cube it, right? 0. And this, x to the 4th, needless to say, will also go to 0. So in the end, as limit as x approaches positive or negative infinity, f of x divided by g of x will equal 1, right? And I should note that the definition for the end behavior model, I actually have it right here, so you guys can actually pause your video for a second and just look at it, right? And it reads, the function g is a right end behavior model for f if and only if, right, limit as x approaches infinity of f of x over g of x equals 1, right? It has to equal 1, like this. This is a right and left behavior end model, right, because it equals 1 and it goes to positive or negative infinity. And likewise, a left end behavior model of f or a function g is a left-hand behavior model of f if and only if limit of x approaches negative infinity of f of x over g of x equals 1, right? So I'm going to end today by doing, once again, another example of the behavior models, and you're going to see how we can apply these in a broader scale, right? So I'm just going to do example 7. This is B, right? So I'm going to do g of x, right, equals 2x to the third minus x squared plus x minus 1. All of that divided by 5x to the third plus x squared plus x minus 5. Right, so your 2x to the third is the end behavior model for the numerator of g, right, because it is the highest degree polynomial. And then your 5x cubed is the one for the denominator, since it is also the highest degree polynomial, right? And you simply divide these two polynomials, and you get 2 over 5. So this is how your function will behave as your x gets really, really huge. Okay, so Mr. Wilson will often use a money example. So suppose he gave you $1 trillion, right? That would solve the national debt. If he gave you $1 trillion and you cubed it, and then he took away $1 trillion squared, and he gave back $1 trillion, and he took away $1 from that. All of that, you would divide it by 5 times $1 trillion cubed, which is huge, plus $1 trillion squared, plus another $1 trillion, and from that he's going to ask for $5, right? And in the end, you're going to come up with an example that's come up with a function that's very, very close to this, which means that as this approaches, as your x gets really huge, this is what's going to model your behavior. All right.